And we'll move now to our next speaker, who is Quanling Deng, who's going to be talking to us about superparameterisation of Arctic sea ice floes.
Hi, everyone. Thanks very much for the introduction. Thanks, organizers. It's great pleasure to be here. Especially thanks, Jody, for the emails. Otherwise, without your email, I would not know this short workshop. So it's exciting to be here. My name is Quanling Deng. I'm from the School of Computing at the Australian National University. So I'm a lecturer at this School of Computing. So before that, I was working at the Department of Mathematics at the UW Medicine. So this is actually a continuing work on the projects that I started at medicine. So this is a joint work with Professors Nan Chen and Sam Stetchman. So let me talk about the project. This is part of the MURI project in USA. This is on sea ice. And the topic of this project is mathematics and data science for improved physical modeling and the prediction of the sea ice. So in particular, this is a 5-year project, and they involve several institutes. For example, at a current institute that Dr. Golden mentioned that one of the students is working in this area as well. And then I will mention a little bit about the particle multi-scale modeling from this group. And also I will talk about the disparate element model developed in this group from University of Washington. And then in our group, which from Wisconsin Medicine, so we worked mainly on this discrete element model, and then the data assimilation, uncertainty quantification, and then this multi-scale modeling, so which I will talk about today. So background, this is outline. So background, I will skip this part. I think this is well introduced in the previous talks. And then I will go to these 3 major contributions from our team. So the first part, which is done at medicine, which is the sugar flow parameterization, and then the 2 multi-scale models, which is kind of like try to couple the particle model and the continuum model. So, and then the first one, which is mainly developed at the NYU, and then the second one developed at medicine. Okay, so sea ice models, so background. So kind of skip this introduction. Basically, this is about the continuum modeling, considering the sea ice as materials like viscous plastic or other kind of type of plastic material modeling as a continuum models. So again, this is one of very nice paper that published recently, and Dr. Golden mentioned this as well. I read this very well. This paper very interesting to read. And then on this direction, so I would like to mention briefly as a kind of motivation of what I'm going to present today is that this workshop happened in 2019 in the European countries, and then the main outcome of this workshop is summarized in this paper. And then some key points here is that the first one is that these continuum models remains a useful tool. By useful tool, I think in that paper, the underlying kind of conclusion is that right now, the continuum model is still kind of dominant in this whole field for all this kind of GCMs. And then the second point is that the particle models, like discrete element models, is a kind of promising avenue. And then right now, today, we are going to talk about mainly focus on the particle models, and then trying to borrow some information from continuum model, trying to do the coupling, and then to see how accurate our multi-scale models. And then some other points which are not really important for this talk today. And then, so looking into the particle feature of the sea ice, so basically this is an image taken from LASA, and then we can see that there's particle features, and then we have different scales. I will talk a little bit more about these different scales in a second. So here, with these particle features, we want to model them, and then this comes with the other models kind of as an alternative for modeling the sea ice, which is flow-based models, so particle models. And this particle models is mainly based on the Newton's second law derivative with respect to the displacement, it goes to the velocity and then the momentum kind of type of equation. So with this kind of DEM model, it can capture a lot of features of the sea ice. For example, the collision, ocean, atmosphere, drags, forces, and the angular momentum, fracturing. So in particular, like Hui from Current Institute worked on this fracturing part on like each of these polygonal shape of ice. So other features also can be captured in this kind of DEM model. So one of the first paper I read on DEM models is this paper by Dr. Herman. When I just got started working this area, which was like about 2 years ago. So how to represent these ice flows? So one of the ideas is that to represent this sea ice as cylinders or bonded cylinders. So this we have some bonding force on these two flows. And then this is one of the images that I took at the very beginning in my project. So I took an image and then tried to use some software to generate some sort of these cylinders. So this is the first idea to represent this ice flows as kind of cylinders and also the bonded cylinders. So here in this work, this fracture behavior has been successfully simulated. So other ideas to represent ice flows. So one of the other one is this finite element type of method. So considering one type of like a polygonal shape of this ice, they each of these ice can be discretized kind of as a subdomain into like 25 elements. So this work is done in this paper in 2015. So this is using finite element type of idea to represent the ice, and we've been trying to match the physics quantities of these flows. And then within our team, so what we did is to represent these flows as polygons of each flow. So we have many polygons, and this is one of the major work that has been done in at the University of Washington. And then we kind of took this kind of model, and then for this data assimilation and other type of work that we are doing. So take a look at the comparison of this continuum and the particle models. So what are the differences and then the common size? So the continuum model has a longer history, reasonable accuracy on large scales. So this continuum assumption breaks down on smaller scales. So in particular, if we look into the meets, right, then this continuum assumption breaks. So for flow models, it has much shorter history, and then these flow scales are kind of represented. It can capture like in the smaller scales, and then but the problem is that it is much more expensive in the computational side. So the question is, can multi-scale models overcome these challenges? So that's kind of a goal. And then multi-scale models. So the first few things that is to look into these different scales. So this slide is basically showing that CS has a multi-scale feature. I think this is well understood in this workshop. So our goal is to kind of effectively represent the flows of different scales, taking into consideration both the continuum and the particle model. So take a look at this fluidity number, which is for the flow regime, where basically this shows that if we have a particle model which represents anything in the physical world, if this fluidity number is really small, then we can use kind of continuum models, so like Navier-Stokes equations or Euler's equations to represent this physical process. If this fluidity number is large, like in the scale of like 100 or more than that, so then people use Boltzmann type of equation to represent the flows. So in this case, in sea ice, we observe that roughly this sea ice flows can be in this kind of transitional region of this kind of model. So this gave us kind of a general picture why we should consider something like combination of the continuum type of model and this kind of particle type of model. So the main idea here, the first one is the superflow parameterization. So this is a Lagrangian type of parameterization. And then there's the other two models, which couples these two situations. So superflow. So this is the idea is very simple. So the basic idea is to treat a cluster of small flows as a superflow, and then we reduce the computational cost. So here the goal is to look into the data assimilation technologies, trying to recover for example, the ocean current, the large scale modes of this. So what I present here is like super oversimplified kind of a model. And the goal is just trying to kind of recover using some data assimilation tools to recover the ocean kind of mode. So test the model. So super simplified. This is a super simplified DM model. So this displacement, angular displacement, momentum, angular velocity. So here, this term here, Fa and Ft, it's coming from the flow contact forces. And then the other piece, this is like a kind of term which is corresponding to the ocean drag, or we can add one more term, which is for the atmosphere drag. So this is kind of linearized the force, just for simplicity here. So the goal is here again, just to do data assimilation and parameter estimation. And then later on, we look into the multi-scale model. So going to a little bit more details on this superflow. So we kind of group together a cluster of small flows into a superflow. So this example here on the left side, we have an original DEM model. We have 200 flows. And then these red circles represent the large flow. The green ones are representing the small flows. And then we group these green flows as like 30 blue flows. And these 30 blue flows, we call them to be superflow. So it's very simple idea. And then what we do is that we cannot just randomly try to group all these small flows. So we put some physics constraints. And then this physics constraints is try to using this superflows to preserve some of the physics quantities. For example, the mass, concentration, momentum, angular momentum. And then with that, we generate this kind of superflow. And then one point to make here is that once this superflow generated, then we can use the same code, same DM model, just try to run a new set of flows. So in the implementation side, it's super simple. And then this is a comparison on the computational saving. So basically, it's a full system has need to use much more time, and then the parameterized system less time. So this is on a case of the data assimilation case, lots of ensembles here. And looking into a bit of statistics. So what here says that is that the parameterized superflow parameterized system captures better statistic quantities of the original system. This is the key message. If without kind of the small scale features, then the statistics is represented by the gray lines, and those are worse statistics. So that's the key message. And then look into the kind of uncertainty quantification, how well this parameterized system can evolve with respect to time. So again, this message here is saying that this parameterized system capture better than the barely truncated system. So barely truncated system is just a simple case where we just simply remove these small scale flows. So data assimilation. So data assimilation, what we used here is that we used some common filter, ensemble common filter, to recover the ocean mode. So one of the case is this small scale area. We have this left column shows the original DEM models, which the original DEM model, how it performs, like how well it captures the ocean current. And then the right column here in this left figure is showing the superflow parameterized kind of system, which the ocean current, as we can see here, captured pretty well, especially when we compare to the case with the bare truncation. And similarly, if we have like a smaller, larger scales, different ocean velocity field case. This is. So that's about the flow parameterization. So it was super simple thing, and then the goal was trying to understand a little bit the larger scale of the ocean. Now looking to the particle continuum super parameterization. So this is basically the idea is to trying to combine the best of two parts. One is the particle part, and then the other one is the continuum part. So superparameterization, this idea was mainly coming from like the atmosphere, the community, where it's kind of a terminology which is kind of equivalent to multi-scale in some sense. So the idea is ensemble like fine scale in each core grid cell. So for example, in atmosphere or ocean dynamics, the model, they use both like continuum model on both like fine scale and coarse scale, and then they couple with each other, try to improve the simulation efficiency. So here on sea ice, we are different. It's a more different situation in the sense that we are using the continuum model for the coarse scale, because we know that for the larger scales, the continuum model works pretty well. And then on the fine scale, we use flow model, which is a particle model. And then the question is, how can we interact with these two models? How we couple them? So this is the challenge: how to propagate this particle information into this macro scale model. So the idea is that the connection is from flows to continuum. So basically, I took kind of the information, the image that I showed earlier about the Claudius number, where if we have the Claudius number moves to a small region, then this goes to a continuum model. Otherwise, we just look into the Boltzmann equation, assuming that there are lots of particles. So the key idea here is that we consider the distribution of flow sizes, thickness or velocity. So we have a large field like these physical quantities. And then this F represent a PDF, like a density function. Basically telling us that at what kind of location, what's the probability we would have. So this is different quantities, and they look into the moments of the distribution, and that's give us, like, for example, if we integrate over the velocity field, then we get the mean ice velocity. So that's a kind of example here. So the first model, so this model was developed in a team, but at NYU, at the Current Institute. And then this model, the idea was that they decompose the probability density function into marginal and conditional densities. And then the marginal density somehow cascade, interpreted as kind of macro scale, so large scale continuum model. And then the micro scale, so smaller particle scale, is for this kind of conditional densities. So they, using this kind of decomposition, they come up with a coupling model trying to get a structure of the two-way interaction between this continuum and the particle model, based on using this kind of Boltzmann equation idea. So this is the Boltzmann equation on the right-hand side. That's the kind of the represent the contact forces among all this. Okay, gotta be hurry. So the second model is, which is this this model that we developed at the Wisconsin Medicine. So this is a coupled model, which the goal is to do coupling with the atmosphere and the ocean. And then what we did, So I can skip this slide, I think. Just this is a comparison between these two models. And then this is a key slide showing this coupling. Basically, there is integration over the probability density function, and then end up with kind of a Navier-Stokes type of equation where we have an extra term, which is the stress tensor. This stress tensor is some information about the flow and flow contact forces. So here, when we couple, this stress tensor part is coming from the statistic of the fine model. And then on the particle model, so we use the multi-scale information to update this fine scale model. So some preliminary results. So basically, this result shows that if we just do this simple coupling, we can get a linear order convergence to the original system from the DM, just the simple DM. So we consider like 100,000 flows in this case, and then we showed this linear convergence. So there's other examples. This is like flow smashing to a coast. In this case, we capture similar behavior on the L2 norm. So this convergence, linear convergence, is all in L2 norm on the sea ice concentration. So this is a different simulation scenario. Let me skip it. So in summary, so I talked about superflow parameterization and then some multi-scale models for this oversimplified particle models. Thank you very much.
Thank you, Quanling. Any questions in the room or online?
Yeah, thanks for the interesting talk. I'm wondering about when you combine the flows to make the simulation run faster, doesn't that have a lot of negative effects on the thickness redistribution from dynamical interactions between the flows?
Yes, it does. It does. Yeah, in fact, at the very beginning, when we look into the statistics, it affects a lot on the, for example, like the flow size distribution. Automatically, you would not expect it anymore. There's kind of power law distribution that's already.
And the thickness as well. I think that's. Yeah,
thickness here. So thickness in this work is oversimplified. We just kind of unify.
I understand.
Thickness.
Thanks.
And then, for that, but then what we do is that we also consider that for the superflows, like the physics quantities, like for example, Young's modulus, those parameters are scaled accordingly. So if you have global flows, then it's more easy to squeeze things like that.
Yeah.
So the constant will be different.
Thank you.
Thank you.
Any more questions in the room or online?
Hi, thanks for your talk. With your non-dimensional number, which I forgot the name of already,
yeah, so,
where do we typically sit for the sort of applications that you were showing? I missed that. So there's a mean free path and a physical length scale. You have a ratio.
Yeah, so all these physics quantities I hided basically is not here in any of my slide. So the title, why I say it's article, it's basically because of that, some of the parameters are taken from the article CI's property. So in our whole team, there's a group of people from Yale University, and then they gave us like all these parameters, and then we scale them to our simplified model. So the parameters will be hidden here.
What is the mean free path in these applications?
So the mean free path is basically if you have a flow, kind of in a statistic sense, the flow traveling to a region before you hitting into a collision with another flow.
Right. Okay. It's clear. Yeah. Okay.
And then over your scale. So
but it's flow collisions. Okay.
Yeah, we look into like the MIS, like marginal ice zone. And the other zones, like these parameters would be just super small, right? If you have a whole,
so it depends on
region,
concentrations, velocities.
That's a small number. And in the marginal ice zone, you have a larger number.
Okay, thank you.